Good morning, everyone. Welcome to Lab 10. So, Lab 10, March 31st, already April. So, let's talk about first, it's just kind of, I wanted to mention a note, which is that the Heartbleed vulnerability is an implementation bug. And it's not a specification bug. I know most of you know this already, but a couple people were confused, and this is the kind of thing that you really want to be careful to know is like what actually caused a vulnerability when you're looking at one. So the second thing that we're going to talk about a little bit today is forward secrecy, just kind of defining forward secrecy. And then just looking ahead, we're going to talk about zero RTT. And finally, hopefully we'll have time to talk about distributed trust. So today's lab is a lot about kind of attack models and security properties and attack models. So in some sense, it's much more of the crypto backing to some of the things you're learning right now. The first thing just being the definition of forward secrecy, which essentially means, so let's start with that, right? Let me just write that down here. Forward secrecy is when your future or your current interactions are protected from future corruptions. Current interactions are protected from future corruptions. What does this mean though? Even if a future corruption leaks the party's entire state, which includes, let's see, future corruption of the party's state, this could include long-term secrets, session keys for ongoing sessions, etc. Right? Then like this is what could be leaked. And what's protected is closed sessions or past information and or past information in the ongoing session. So how exactly a session is defined and how far in the future the session is protected depends on the protocol. Forward secrecy is a general notion that in the interactions that you're having now are protected from future corruption of the client state. But when you hear about forward secrecy, you do want to always ask the question of when does the forward secrecy kick in, right? So does it, the last message that I sent, does it become protected the second that I send a new message? Does it become protected, after I close this session and start a new session? When does it become protected? Right. And so let's discuss something that isn't doesn't follow forward secrecy, right? So what happens in static Diffie-Hellman? In static Diffie-Hellman, we never get forward secrecy, right? Why do we never get forward secrecy? We never get forward secrecy Precisely because the long-term key of the party is stored in its state forever, right? So as long as it's using that static exponent B that's on the certificate, so say we have a certificate, it has, the public key, G to the power of B, and it also has its kind of signing key, or technically it has its verification key because the signing key is secret, right? And this is a certificate, so we have the seal of approval on it, right, with like the CA's signature. Then as long as the party keeps using this certificate to do static Diffie-Hellman, then it's going to be storing this exponent B in its state, right? So the state contains B and it also contains a certificate. At least we know these things. So if there's a man in the middle attacker that has seen the communication between me and this server that has this certificate, and we use static Diffie-Hellman, then it has my public value, which is say G to the power of A that I sent to the server. And as soon as it learns this value, right, as soon as it learns B, what it can do is that it can compute the key that we computed, that we used for our communication. And once it can do that, everything about the communication becomes visible to this adversary. And so forward secrecy never holds here as long as this certificate and this key pair is in use by this server. This is why static Diffie-Hellman is bad. How does ephemeral Diffie-Hellman protect against this? It protects against this precisely because after the server and I have agreed on a key, the server is going to delete this exponent because it doesn't need the exponent anymore. Because the next time that it starts an interaction with a new client, it's going to use an entirely new pair to agree on a Diffie-Hellman key together. So I hope that clarifies what forward secrecy is. The high level idea is just that your current interactions should be protected from future corruption. And the specific details of how this becomes true is dependent on the particular context in which you're achieving forward secrecy. It depends on, the security definition exactly that's being used, or, what the protocol is actually trying to say. And this is true in general, for security definitions. You do want to ask what the details are. Even if the details are fairly standard, if you don't know them, it's important for you to find them out so that you can accurately reason about them. Okay, so the second thing that we're gonna kind of quickly actually go over after forward secrecy is the concept of zero RTT. This very briefly, I'm just going to talk a little bit about it. Right, so zero RTT is a trade-off, right? What is it a trade-off between? It's a trade-off between latency and security, right? And the trade-off looks something like this, where if we're using zero RTT, we're kind of looking for a little bit more of one thing than the other, right? What are we looking for more of? We're looking for more of a reduction in latency. So maybe we write this in this color. So a reduction in latency over what? We're looking for more of a reduction in latency over, the security guarantees. So what's the trade-off? What breaks when you're trying to get a reduction in latency using something like zero RTT? What breaks is that you now enable replay attacks. So now we have this thing that's possible that wasn't possible before, and that's kind of the reduction in security. And so for this reason, this may not seem like a problem some of the time, which it isn't, right? If you're kind of just loading a static page and the request that you can replay is a request to load a publicly available static page, then that seems like it doesn't hurt so much. Whereas if you were using the 0 RTT to make some sort of payment, then that's when it turns into a problem. So what's true is that we have to be careful, right? So we must be careful about what we use 0 RTT for. So we discussed some examples right now, right? And so maybe I'll use a brighter green. The example of something that worked was, loading public static page, or rather getting public static page, versus what's one situation in which it would be bad to use 0 RTT. That's going to be, say, payments or money transfer. Right. So why is this true? Getting a public static page, if we replay that request, right? If we replay the GET request, then that's not so much a problem. Whereas if we replay a request to make a payment or to confirm a money transfer, then that's very much a problem, because that's when we kind of are allowing the adversary to cause something to happen in the real world that we really don't want happening. Right. So what could happen here that would be bad? And let's see an example of that. So we're going to have some client here that's just trying to make some sort of request. And we have the server on this side, and we've got some adversary sitting in the middle. Right. So what can happen is we can have the client can send a client hello over 0 RTT, and then send a request to, post or send money. And what the attacker can do is it can take these requests. Let me see if I can grab the whole thing. Maybe not. Okay, so it has to post or send money. And then the attacker can take this and replay it a few different times without making the server suspicious. Third time's the charm, right? Okay, so here we go, right? And so it can replay this and cause bad things to happen. So we want to make sure that we're kind of protecting that use case and that we're not allowing zero RTT to be used in those situations. Finally, we're just going to move on to distributed systems and really kind of discussing a little bit about trade-offs in distributed systems and just some inherent properties of a distributed system and how to get trust in a distributed system. Because kind of what we've been doing throughout this course is we're talking about network security, right? So we're operating in a distributed system and we want to get some guarantees. We want to get some confidentiality guarantees. We want to get some authenticity guarantees. We want to ensure some sort of reliability over the internet, right? And there's many different ways to get this. And we're moving from one way to get this, which is centralized trust, to another way to get this, which is, much more decentralized trust. And we want to talk a little bit about why that might be good or bad, right? Because there's arguments to be made on either side, and it's a little bit nuanced to understand what's going on here. So the final point, I don't know how many points we've gone through so far, I think this is 4, is distributed systems. When a system is distributed, it can be much slower to propagate change. So already we get kind of an intuitive sense for this in terms of updates, right? So if something is centralized and the central location needs to update for all parties to get the benefits of the security update, then that can happen immediately as soon as the central authority decides to do that. Now, if a system is slightly more distributed in that each of us have an app or an iOS or something like that on our devices, and we need to update it to get the newest security guarantees, then that can take longer. It can be helped along though, right? So how can it be helped along? With, say, WhatsApp, it can refuse to load the app till you update to the newest version of WhatsApp beyond a certain threshold, right? So same thing with, the OS on your system is it can refuse to load or it can kind of force an update, which happens sometimes, much to our chagrin when it happens in the middle of a class. But generally, it causes the system to update and uptake changes faster. The other aspect of distributed systems is that we have this opportunity when we're trying to get authenticity and confidentiality to really distribute the trust as opposed to choosing to centralize the trust, right? And allow people to kind of authenticate that over time. This has some trade-offs associated with it. Right. So the more we centralize the trust in a distributed system, we've already seen that it makes it faster to propagate changes. But also, the more that we centralize trust, we get this trade-off between, we're centralizing trust. And so these systems become truly opaque, even to, very skilled users. But at the same time, it is very clear to all users of the system that the system is opaque. So there's some concern about the fact that when we move to distributed trust, sometimes people can believe the distribution of the trust at face value. So one of the very good questions that we got asked a few times in the weekly questions this week was what happens for Tor, for Onion servers, when you when an adversary can control, say, all the entry nodes of a system? This is a very good question because it gets to the heart of the issue, right? So when a system is distributed, it can be slower to propagate change, but also so this is when a system has distributed trust, it can be slower to propagate change. When a system has distributed trust, another thing can happen. And this is kind of like a good versus bad, right? It becomes less opaque to very skilled users, right? So there are now people out there that kind of don't work for a particular company, even if there is a particular Bitcoin company that has a lot of this power. The system is less opaque to other people, and it is possible for people to go and make their own checks and really make sure that things are happening the way that they expect them to happen, in a much kind of deeper sense than we get in a more like centralized trust system, right? But what also happens is, it gives the illusion that we can take the distribution of trust. We can take the distribution of trust at face value. And this is not accurate. We cannot always take the distribution of trust at face value, because what happens, when somebody controls a big part of a distributed system, we've distributed trust. And so if they can control enough of the system, they can mess with the system, right? And there is some kind of inherent bounds there, and we can talk about that a little bit in a minute. The important thing is, while it becomes less opaque to very skilled users, it can give the illusion that we can take the distribution of trust at face value. Oh, right. So this would be a con. Is that we're giving this illusion. So this is kind of the main nuance there. And so the idea here is not to kind of have you learn this like very specific line, right? The idea is for you to understand kind of the world in which we're operating, right? So we're operating in the world where we're in a distributed system. One of our options for getting trust and building security guarantees is to centralize that trust. And when we centralize that trust, then we can have like faster updates, and we can kind of have less of an illusion that the power is distributed, and we can kind of think about that more critically. But what's also happening is that centralized trust means that we have, centralized trust. So there's a whole lot of power in that central authority, and perhaps we don't want all the power concentrated in one place so deeply. Also, the system becomes very, very opaque, right? So for centralized systems, like I don't know, for say a lot of the software that Apple rolls out, right? We don't actually have a way of checking that they're using the protocols that they say they use, the way that they say they use them. Of course, we can try to attack the protocols, and this gives us some sense of trust that they must be really doing this, but we can never really be sure. And as we distribute trust more and more, it becomes less opaque to very skilled users. Maybe very skilled users can go ahead and bolster their security guarantees a little bit more, or make more checks to make sure that things are really operating the way that they want them to. So we have this. The only kind of slight concern there is that it can give the illusion that we're distributing the trust, that we're distributing the power, but sometimes this doesn't happen, right? So maybe in the case of say NFTs, organizations can come up that, then you're always using these organizations to check the authenticity of an NFT. And that kind of puts a lot of the trust into this organization that's providing you that verification. Or in the case of say Tor, maybe if a particular large power in the world wanted to kind of break the anonymity of Tor, it could potentially go ahead and gain control of a lot of key nodes that are going in and out of a particular location on the internet, and it could break anonymity in that sense for that network traffic, right? So maybe since we have a little bit of time, I think still, we can discuss a little bit why it may be inherent that we can't always guarantee that a malicious party who can gain control of a lot of the system can't game the system. Why can't we guarantee that, right? So the reason why we can't guarantee that, so maybe I'll start by writing that down, right? So why can't we guarantee that an entity that has control over a large part of the system still can't do too much to break it, right? So why can't we guarantee this? We can guarantee this in a centralized system, right? So in the centralized system, what we can do is we can say that even though there's this very big company that is doing all of this stuff and has all of this power, the centralized system, say the certificate authority that gave the other certificate authority this power, can say, I don't trust this system anymore, so I'm going to build checks and balances so that people know not to trust this entity anymore, or this set of entities anymore. What happens in a distributed system is inherently, once you gain control of enough of the system, it can become impossible for a user to guess which parties are malicious because of the fact that this trust is distributed and everybody is just as trusted as each other, right? So to understand more about that, think about it as how, inherent phishing is to breaking the trust of, say, something like encryption or, any other protocol that you're running over the internet. That's kind of the analogy for how controlling a lot of a distributed trust system can break the trust of the system, right? Because you're breaking kind of the underlying assumptions, right? So the underlying assumption on which a lot of cryptographic protocols are built, like encryption, is that your keys are secret. So if somebody can conduct a phishing attack and get your credentials, right, your private credentials, then they can break that property and effectively kind of break the security that you're getting from the system. And this isn't because there's something about the system that's breaking, it's because we're really kind of going outside the system and breaking the assumptions that the system is based on. And so similarly, in a distributed system, we need to assume that a particular fraction of the system is trusted. And if we can't do that, then that can really become a problem. And so once we get kind of cryptographic tools, the amount of the system that we need to be trusted is a majority. So we need an honest majority to get security guarantees in a distributed system most of the time, depending on which security guarantees you're looking for. So let's talk about that, right? Where does that come from? Let me pull a picture from a different document. All right, so I'm back with the pictures that I said I was going to grab. And what we're going to do is we're going to talk about the Byzantine generals problem. And this is, something good to know because it comes up a lot when we have discussions about distributed systems. And the idea here is we have, a bunch of generals from this army that are camped outside cities, and if they all attack together, they will succeed. But if they don't attack together, right, if some of them attack and some of them don't, then their attack will fail. So they really need to make sure that they have consensus before they attack, right? So, we have all these generals and they're communicating, they're trying to make a decision, and they pass along the information that they heard from, everyone around them to everybody else that they're talking to kind of get some sort of consensus, right? So we try to do this. And what I'm going to do right now is talk about why that idea might break for 3 people, right? So say that we have 3 people, right? Let me grab those 3 people real quick. How do I do this? Yeah, okay. So I'm gonna grab these 3 folks right here. So we have these 3 generals, and they want to agree on attacking before they attack. And so we want 2 things, right? So we want that all honest generals agree on whether to attack or not. And then the other thing that we want is that if all honest generals want to attack, generals think they should attack, then they will all agree to attack. And what we're going to see in the example is that we're going to have this trust kind of break down. We're going to see 2 different examples. One, we're going to see 2 different examples from the perspective of this one party. Maybe I'll highlight this one a little bit. And I'm going to highlight this party slightly. And we're going to see 2 different things from the perspective of this party. One where this guy is malicious and one where this guy is malicious. And we're going to see that the party can't tell, they can't tell whether the person to their right is lying to them or this general above them who's giving the instructions is lying to them. So let's see what happens, right? So in the first version, we have a command come down from here that says attack to both the left and right generals. And then we're going to have this left general say to the right general, he said attack. And the right general is actually malicious. So they're gonna respond. They're gonna respond and they're gonna say, they said retreat. Right? And so now this party right here that we had highlighted a minute ago is in a conundrum as to whether they should attack or they should retreat. And why is this the case, right? So what could be the situation? So here, what we want is that since this party is malicious, we want this party to decide to attack because all honest parties must agree at the end of the protocol, right? And so what could be the situation that the party is worried about, right? What is this general worried about? And let's see what that looks like. What are they worried about? So what is this party worried about? They're worried about this situation, right? Where actually the person that sent down the command is the one who's malicious. And what this person did was tell one person to attack and the other to retreat. And so in this situation, also the party is going to see an attack command come from the top, and they're going to say, the commander told me to attack. And they're going to get the response from the party on their right-hand side that says, the commander actually told me, and maybe I should make this picture slightly smaller so it can fit on the screen slightly better. Right? And so they're going to get a message from the right that says that I actually got the message to retreat. And what we want here is that this party right here that we had highlighted a minute ago, right? This person would want to output retreat here because we need the honest parties to agree, right? And so this is the conundrum that we're going to have, and this is why, beyond a certain threshold, we can't guarantee that all honest parties will agree on the output of the protocol, which is called consensus, right? We can't guarantee that we're going to have consensus because in a situation like this, what is the party going to do? They don't know, because their view looks the same in the top and the bottom world. And why is that? Is because they're not seeing this message, right? So they can't tell who is lying. This message is kind of hidden to them because it's between two parties, neither of which they are. So what's happening is they can't tell who is malicious, and so they can't make sure that they agree with the honest party. Consensus is difficult to get or not possible to get unless we have an honest majority. All right, thank you so much for watching Lab. I'm sorry that this was posted slightly late. I hope that this is helpful and it clarifies some questions about just security models and zero RTT, forward secrecy, what's going on in all these places. Please post questions on Piazza as they come up while you're watching this video. And thank you very much for watching this video.